Hey guys, welcome to my talk. My name is Pan Du, and I'm from the Department of Aerospace and Mechanical Engineering in University of Notre Dame. And today, I'm going to present my recent progress of the Bayesian data assimilation for cardiovascular flow using a biofidelity ensemble Kalman inversion. So to begin with, I would like to introduce a bit of background information about my study. So the problem is in the problems in diagnosis of cardiovascular diseases. One very effective way is to use the image-based CFD simulation, and it is very popular because it can provide comprehensive hemodynamic information, such as the flow field, the Gaussian stress distribution, as well as the pressure distribution. But it has some shortcomings as well. So one very important point about the CFD simulation is that the accuracy of the results are highly dependent on the boundary conditions and the input parameters. So in many cases, such input variables and boundary conditions are very hard to obtain, such as the inlet velocity profile of a vessel, or the stiffness of certain material like the vessel wall or the heart wall. So even if you can obtain those parameters, they also contain a certain degree of randomness. So quantifying the uncertainty of those parameters is also very crucial to apply to those models in clinical situations. So in a lot of simulations, we are forced to infer those unknown parameters from other information that is accessible. So this kind of problem is always called the inversion problems in cardiovascular flow. So here we can see a basic example of this inversion problem. So to begin with, this is a geometry of an aneurysm bifurcation, which is a very common cardiovascular disease. So the flow goes in here, and it bifurcates into two channels. And the right side is a abnormal shape, which is the aneurysm. So if you know the input velocity profile, and you also have some scans of a patient using the MRI. So here the MRI refers to the magnetic resonance imaging. You can actually reconstruct the geometry and set all the boundary conditions and give the inputs to a CFD solver, and you can easily get the flow field information. You can also get the ball shear stress, and you can also get the pressure distribution. But what if we don't know anything about the inlet velocity field? We only have the geometry of the model, and also we have the sparsely and noisy flow measurements of the flow field. And those sparse and noisy flow measurements can be obtained from PCMRI, which is referred to as phase contrast MRI. So it can give velocity magnitude in all directions in the flow field. So the problem is that how do we incorporate the sparse noisy flow measurements with our CFD forward model so that we can give a prediction of the 3D inlet velocity field. So we can actually do this by formulating the problem according to the Bayes rule. So here, theta represents the unknown parameters in our model, and the capital F represents our CFD model. And if you give a parameter theta and the initial state of the field, you can use the forward CFD simulation to get the simulation results. But here, the simulation results consist of the ground truth and some kind of uncertainty, sigma m. And here y represents our observation of the data, and the y equals to hx plus sigma d. And h here is actually an observation operator, which extracts a limited dimension of data from the ground truth. And it is also blended with some kind of noise sigma d. So finally, if you give a prior of the theta, and you can actually calculate the posterior of the unknown parameter theta because it is proportional to the prior of the theta multiplied by the likelihood function. So we can actually realize this Bayesian approach by using a Karman update. But in order to use the Karman update, we have to give two very important assumptions. The first one is that we need to assume that the formal model is linear. And the second assumption is that we need to assume that the prior and the likelihood are all unbiased Gaussian distribution. So using these two assumptions, we can actually get the analytical solution of the posterior. And here, here is the formulation outlined in the red box. So using this formula, we can actually update the state X by a weighted innovation. And those weights are actually based on the covariance of the hidden states and the observed states. So in order to achieve this, we actually need to calculate the first and second momentum of the prior by sampling. So we actually need to sample the prior distribution to obtain the ensemble of the prior. And we propagate those prior ensemble via this Karman update to get an ensemble of the posterior. And here, the ensemble size don't need to be large. Typically, a number less than 100 is large enough to give a very good approximation of the posterior distribution. So another problem about this model is that in practical use, we actually consider the form model as the self-decimation, but self-decimation is very unlinear, which contradicts the first assumption that we used in the previous Karman update. So the Karman update actually becomes suboptimal. It is not optimal anymore. So in order to give a very good, accurate posterior, we actually have to do this in an iterative way. So the actual steps are, first of all, we have an initial guess of the prior, and then we propagate it through the forward prediction model. Then using the Karman update, we can get the updated ensemble posterior. And then we substitute the posterior to the previous prior, and then we put it into the form model and Karman update again. So using this iterative method, we are actually constantly updating the theta distribution to let it approach the ground truth step by step through the iteration process. So this method can also be formulated as the following constraint optimization problem. So it is actually minimizing the difference between the projection of the state and the observation data, and such that the actual state is actually equal to the form model given the true parameter of the model. So theoretically, this method can give a very accurate prediction of the mean of our unknown parameter theta. However, it has another problem. So usually the safety simulation can be very expensive. So this method is actually constantly putting parameters into the safety form model and conducting safety simulations again and again. So the computational cost of this method is actually proportional to the number of iterations multiplied by the number of our ensemble size. So it can easily be computationally prohibitive. So how can we reduce the computational cost in this method? So one very intuitive solution is that we can just substitute the self-decimation with a very coarse, low fidelity solution. So one method, one example of changing a high fidelity solution into a low fidelity simulation is that we can just change the mesh from a very dense mesh to a very coarse mesh. And in this way, we can largely reduce the computational cost of our model. However, the low fidelity model can predict results with very low accuracy, and the inferred results could be very wrong. So a smarter way to do this is that we propose a bifidelity model. A bifidelity model is actually combining the high fidelity safety simulation and the low fidelity safety simulation. And this bifidelity strategy actually leverages the accuracy of the high fidelity model and also the efficiency of the low fidelity model. So by using the bifidelity model, we can actually give a very accurate prediction of the posterior of the theta with an acceptable cost. So here is a diagram that is illustrating how the bifidelity model works. So here you have a parameter space with a lot of sample points within it. And you can propagate those parameters through the low fidelity model. So the low fidelity model can be realized by simply using a very coarse mesh, or you can set a very loose convergence criterion in the simulation. So because those low fidelity solutions are very cheap, you can actually get a lot of samples, and it can well represent the whole solution space here. So from those sample set, from this sample set, you can actually select some very important points from the samples. And here, I want to simply briefly introduce about how we choose those important points. So, for example, you can set the first point as the mean of all the samples. And then for every next point, you can determine the next point by maximizing the distance between the point and the previous space, which is consists of all the previous selected points. So by doing this, we can actually select very limited numbers of the low fidelity bases, which can represent the majority variance of the solution space. And after we selected the important points here, we can actually conduct our high fidelity simulations over those selected points and get the corresponding high fidelity basis solutions. So here, whenever a new parameter comes in, we can actually propagate the parameter through the low fidelity model and get the low fidelity solution of the new parameter. And then we project our low fidelity solution of the new parameter on those low fidelity bases to get the coefficients. And then we simply multiply the coefficients here with the high fidelity basis, and we construct the bifidelity solution. And we get the bifidelity ensemble here. So using this bifidelity method, we can actually predict the posterior with an acceptable cost. And we also have a theorem to evaluate the accuracy of our bifidelity solver compared to the high fidelity solver. So the idea is that the high fidelity solver is actually very accurate. So we evaluate the relative error between our bifidelity model to the high fidelity model. And this relative error is bounded by the relative distance, which is dependent on the selected important point and the previous hyperplane space. And also another part of the error is the in-plane error, which is formulated here. So the actual details of the theorem can be found in the following paper here. So we adopt this bifidelity EKI method and apply it on a test case we mentioned before, which is the aneurysm bifurcation model. So here we have the sparse and noisy measurements from the flow film, and we also have the geometry here we obtained from the MRI scans, and we want to incorporate the measurements and the safety form model to get a very good prediction of the 3D inlet velocity field. So in order to do this, we actually created synthetic measurement data. So those synthetic measurement data is actually sampled from the ground truth, and we corrupt it with some kind of random noise here. So this is the information that we already know. And the unknown information is the inlet velocity. So we're gonna use this model to predict the inlet velocity profile and compare it with the ground truth here. So to quantify the uncertainty, we have to give a to quantify the uncertainty using the Bayes rule. We have to provide a prior distribution of the inlet velocity profile. So here we use a Gaussian process. So first of all, we have a certain deterministic inlet velocity profile, which is U inlet base, and then we perturb this base inlet profile, and we represent this uncertainty using the Gaussian process. It's a kernel function like this. So the fx is actually the perturbation, and it is actually decomposed over some KL divergence, KL expansion modes here. And here we select the KL modes as a number of 6, a number of 9, so that we can actually add the fluctuations back to the base inlet profile to get a prior distribution of the inlet velocity. So since we are only selected 9 basis functions here, so we are using actually 9 KL modes to represent the perturbation. So it is actually formulated into a 9-dimensional inversion problem. So here are some contours of the basis of the prime. And using this bi-fidelity EKI method, we can actually see the results here. This figure shows the error between our prediction and the ground truth as a function of iteration steps. So here, if we use the high fidelity model, it's actually gonna be very computationally expensive. So we have 100 sample size, and we have a total of 10 iterations, and it will take 30 hours for the high fidelity ensemble Kalman inversion method to execute. But for the bi-fidelity model, it only costs 0.15 hours, which is a very significant improvement. And from the accuracy, we can see that the bi-fidelity model actually gives a very accurate prediction of the posterior distribution only after 10 steps of the iteration. But if you use the low fidelity EKI, although you can have a very cheap and very quick update, however, it is not reducing the error as a function of the iteration. So the low fidelity EKI gives a very wrong prediction of the inlet profile. If you look at the contours on the figure below, it is comparing the inlet velocity profile and the vector field between the ground truth, the bi-fidelity EKI inferred, and also the low fidelity EKI. And you can see that our low fidelity EKI is very different from the ground truth. However, our bi-fidelity EKI gives a very close prediction compared to the ground truth with a much more acceptable computational cost compared to the high fidelity method. So the actual mean we obtained from the EKI method is very accurate, but we cannot trust the uncertainty given by the Kalman update, because in order to accurately quantify the uncertainty, the golden rule is always adopting a fully Bayesian method. However, in this fully Bayesian method, the computation cost can be even more expensive, because you have to give a lot of tries to the formal model. So currently we are working on how to further simplify the model to improve the efficiency of the model furthermore. And we are working on developing a surrogate model to substitute the CFD simulation so that it can be made very efficient and even more efficient than this bifidelity model. But in order to prove that our concept is correct, we actually conduct a very simple case to validate our thought. So we basically what we did is that we use the MCMC method and applied on a simple 2D static simulation of outer dissection simulation, so that we can prove that we can use a fully Bayesian approach to accurately quantify the uncertainty of the parameter. So here are the steps of the validation case. The first step is we simplify the case into a 2D static simulation of aorta dissection. So the aorta dissection is actually another very common cardiovascular disease. And we also infer the inlet velocity from our observation data obtained from the flow MRI and also the CFD model. So here is the aorta dissection contour geometry. So you can see that the flow is going into the aorta here, and it dissects into two channels, which is the true lumen here and the false lumen here. And similar to the aneurysm case, we are inferring the inlet profile from measurements and also the CFD model. And in order to further simplify this, we are assuming that inlet velocity profile is parabolic, and we are simply quantifying the uncertainty of the velocity magnitude at the inlet. So assuming that we have already applied the EKI method we mentioned before, and we already have a very accurate mean, which is U equals to 0.6. And then we only have to assign a small interval which is very close to the accurate mean, and we perform MCMC on this interval to obtain the posterior. So here I gave a very conservative prior, which is beta distribution. You can also give a distribution of a normal distribution because you have a lot of confidence in the mean map. But anyways, using this prior, we can incorporate the 40 flow MRI measurements into the likelihood function. And by multiplying the prior and the likelihood function, we can actually get the posterior of the theta and get a very good approximation of the uncertainty of the theta. So as you can see on the right figure here, as we using the MCMC method, the prior is actually changing from a beta distribution into a distribution that is very similar to a normal distribution, and the mean is 0.6, and the uncertainty is accurately captured by our MCMC method. So to summarize, we proposed a bifidelity ensemble common inversion method and applied our method on aneurysm bifurcation case. And the method leveraged the accuracy of the high fidelity model and the efficiency of the low fidelity model, and yields accurate mean inlet velocity profile with economical computational cost. Besides predicting the mean accurately, we have to quantify the uncertainty. So we later on adopted the MCMC method to quantify the velocity magnitude of a very simple 2D aorta dissection case. So this aorta dissection case is used for validation, as the proposed method gives accurate prediction of the uncertainty of the theta, which is the velocity magnitude at the inlet. So our future work will be focusing on applying the ensemble common inversion and the Foley Bayesian method on a 3D simulation, so that we can predict both the mean and the uncertainty of the parameter theta accurately. So that's all of my results. And thank you for hearing. And if you have any questions, you can leave the question on the Slack, and I am very happy to answer them. Thank you very much.